Hi! Today we'll discuss the factors that influence how much of a radionuclide we will produce. To produce a radionuclide, you have to irradiate a target material, which really can be any element depending on the radionuclide you want to produce. Let's take a look at target nucleus A. You can irradiate target A by shooting a projectile, lowercase a, at it, which can transfer some of its energy to it or even get completely absorbed. The target nucleus is then in an excited state and releases some of this excess energy by ejecting a particle or a gamma photon. We call this the ejectile. What we are left with is product nucleus B, which can either be a new radioactive or a stable element, or even a different isotope of the same element. In short, we write this production equation as A, incoming projectile and outgoing ejectile in brackets, and the product nuclide on the right-hand side. There are different projectiles possible, such as neutrons, protons, gamma photons, or alpha particles, depending on whether you are irradiating your target in a nuclear reactor or a cyclotron. Just like there is quite a variety in possible ejectiles. For example, when irradiating an oxygen-18 target with protons, you produce fluor-18, which is an isotope commonly used for medical imaging. And upon neutron irradiation of a lutetium-176 target, you produce lutetium-177 along with the ejection of prom-gamma photons. Let's see whether we can predict how much of a certain radionuclide we would be producing. Next to the irradiation time, the produced activity depends on the flux, or the number of particles used for irradiation, the number of target atoms, and the cross-section, which is a measure for the reaction probability. When we are irradiating a target with neutrons in a reactor, the flux is typically expressed in around 10 to the 13th or 10 to the 14th neutrons per centimeter square per second. The accelerated flux, for instance when irradiating with protons, is expressed in particle microamps, where a medical cyclotron could provide a flux of 20 particle microamps or 1.25 times 10 to the power of 14 protons per second. The number of target atoms can be calculated by multiplying the mass of the target with the isotopic abundance and Avogadro's constant, divided by the molar mass of the target isotope. The number of atoms in your target that is actually irradiated depends on whether you are irradiating your target in a reactor or an accelerator. In a reactor, the neutrons are everywhere, and your target is immersed in this sea of neutrons. The entire target is therefore irradiated. In an accelerator, the beam is generally smaller than your target, and you only need to take the number of atoms in the irradiated volume into account. Finally, the cross-section is a measure of the reaction probability, so the chance the projectile interacts with the target. The cross-section is generally expressed in barn, where 1 barn equals 10 to the negative 24 centimeters squared. This cross-section is different for each different target isotope and incoming projectile. When you're irradiating your target with neutrons, the cross-section generally decreases with increasing neutron energy. So, the highest cross-section can be expected for thermal neutrons, a bit lower for epithermal neutrons, and at the highest neutron energies, the fast neutrons, the cross-section is lowest. When you're irradiating your target with charged particles, such as protons, you can optimize your beam energy to maximize the cross-section. Putting all this together, the rate of production of a radionuclide is described by the flux times the number of target atoms times the cross-section. However, in the time you are irradiating your target, the produced radionuclides also start to decay again. This rate of decay is mathematically expressed by the product of the decay constant and the number of produced atoms. Combining the rate of production and rate of decay gives us the following differential equation, which can be solved to give us this formula, with which we can calculate the produced activity at the end of irradiation. You see that also the irradiation time is taken into account here. Sometimes there is a bit of time between producing your radionuclide and using it, for example, for medical purposes. The activity you have left after this cooling time can be calculated by multiplying the activity at the end of irradiation with e to the power of negative lambda times the cooling time. We'll now use what we've learned in this lecture to solve the following exercise. We have a target consisting of 50 milligrams of lutetium, which is irradiated for 1 hour in a reactor. The neutron flux and some other physical properties of lutetium are given, and it's up to us to calculate how much lutetium-177 we are producing. First, let us consider the reaction taking place. We are irradiating the lutetium target with neutrons to produce the desired radionuclide. Using the half-life of lutetium-177, we can calculate the decay constant. And we find the number of target atoms by multiplying the target mass with the natural abundance of lutetium-176, which is 2.60%, and Avogadro's constant. Then we divide by the molar mass to obtain the number of target atoms. The cross-section was given in barn, which we need to convert to centimeters squared. And then we have all the information needed to calculate the activity at the end of irradiation. We multiply the neutron flux with the cross-section, the number of target atoms, and 1 minus e to the negative lambda times the irradiation time, which was 1 hour, to find a total activity of about 2 gigabecquerels. And now it's time for you to practice. In the following exercises, you will use the equations from this lecture to calculate produced activities. Good luck!